In 1915, when Einstein presented his theory of relativity, along with the theory, he also put forward some predictions. And one of these predictions was the existence of gravitational waves. According to the theory, any object, including you, me, a ball, or even a glass of water, moving through space with a non-zero acceleration, will produce ripples in the very fabric of space. And these ripples will carry energy away from the source at the speed of light. And these ripples are very similar to the ones that we see when you drop a pebble into water.
We need astronomical sources like black hole binaries and neutron star binaries and supernova to produce waves that are strong enough to be detected.
But being measurable does not mean that you can feel their effect. Even the strongest of gravitational waves cannot produce a strain more than 10 raised to the power minus 21. What this means is that if you have a length of 1 meter under observation, then the stretching and squeezing in that length due to gravitational waves will be of order 10 to the power minus 21. And to visualize, it's like varying the radius of Milky Way galaxy by 20 centimeters. And the strain is so small that many scientists, including Einstein, who predicted their existence, used to believe that gravitational waves may never be detected. But some of the scientists did not lost the hope. And because of their consistent efforts, we have LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory, and it's an observatory that lets us measure the distortions in the space-time created by gravitational waves. On 14 September 2015, scientists at LIGO team detected something that shook the whole field of astronomy. What they detected was gravitational waves from a system of two black holes, one having a mass of 29 solar masses and the other having a mass of 36 solar masses, spiraling around each other 1.3 billion light years away from Earth, which eventually collide to form a single black hole of 62 solar masses and released 3 solar mass worth of energy in the form of gravitational waves. And LIGO works on two basic principles. The first one being that whenever two waves combine in such a way that the maximum of one coincides with the minimum of the other, then the result is zero. That is, they end up cancelling each other. If the wave is light, then zero corresponds to a dark spot. If the wave is sound, then zero corresponds to no sound. The second one being that whenever a gravitational wave passes through an object, it stretches and squeezes the object. And if we have a light ray going back and forth a particular distance, then when a gravitational wave passes that object, the distance that the light has to travel will also get stretched and squeezed. This in turn will result in change in time that the light will take to go back and forth that distance.